Great, welcome everyone. I'm delighted to have one of our own speak to us today at the lunch seminar. Cyrill Krähenbühl, said it correctly. I have a tough last name. His research focuses on public key infrastructures and pathway networking. He completed his PhD at ETH Zurich and is currently a postdoctoral fellow with us. His work lies at the heart of CITP's efforts to connect technical insights to complex social and policy challenges. His research introduces flexibility into the trust foundations of PKI, enabling end user and certificate owners to decide their own trust preferences, but in a flexible and available way. I've had the pleasure of collaborating with him on one project related to Web PKI, and we're looking forward to seeing how his work can continue to have a positive impact on real-world security challenges. So with that, Cyrill, over to you.
Yeah, thank you very much for the introduction here. As Mihir said, I've been looking at the public key infrastructure for a few years now, and I have also collaborated with Pratik Mittal from Princeton a few years ago, and I will talk about one of these projects here. So let me start with an overview. So in the first part of this talk, I will talk about the Web PKI, which is a PKI that everybody uses every day, essentially. I will quickly introduce how it works.
I can't hear.
Yeah, sure. So I will first introduce the Web PKI. Then I will talk about some of the problems that it exhibits. And next, I will talk about one approach to solve this problem, which is called trust flexibility. Then I will talk about the paper I mentioned before, flexible PKI, FPKI, and quickly give an overview of how it works. After that, I will quickly compare FPKI and in particular its trust model to other PKIs and their trust models to give you an insight of which challenges we can solve with FPKI and for which challenges maybe other PKIs are better suited. And finally, I would like to have a discussion at the end, an open-ended discussion where we can talk about anything related to my research or anything else that sounds interesting. So let me start with an introduction of PKI. So PKI are public key infrastructures. And here I will show you a very simple scenario and how they can be useful. Imagine we have two users, Bob and Alice, and Bob wants to send a message to Alice, and Alice wants to make sure this message was really sent by Bob. So how can she ensure this? And one very interesting cryptographic approach we can use is an approach called asymmetric cryptography. In asymmetric cryptography, Bob can generate a key pair consisting of two parts. First is a public part, a public key, which he can share with any other entity he wants to communicate with. And the other part is a secret key. It's important that the secret key never leaves Bob's premises, so it's kept safe and is not revealed to anyone. And what this allows Bob is, in addition to the message, he can send his public key to Alice, and he can create a so-called signature over this message using his secret key. I tried to create an analogy here. You can think of the secret key as a key lock, which only Bob can close. So Bob can essentially take his message, put it into a box, lock it with this lock, send it to Alice, and Alice can then use Bob's key, the public key, to open it. It's important that only Bob's public key can open it, and Bob's public key can only open this box. So do we have we now solved the problem of authenticating the sender? No, we have not. So Alice can then open this box, verify that it was indeed signed with the given keypad. And if that's the case, she can be safe, right? However, how does Alice know whether this PK Bob is actually the public key of Bob? Couldn't it be Eve or any other entity just pretending to be Bob and sending their own public key? And the whole task of the PKI is exactly to ensure the authenticity of this public key of Bob. So essentially, the PKI goal is to create a binding between an identifier and the public key. So in this case, between Bob and PK Bob. And this is typically done in an authentic statement called a certificate. So in blue, you can see a certificate connecting Bob and his public key. So now Alice can use this certificate, verify whether the key used to sign the box and the key and the certificate are identical. And if that is the case, she can be assured that indeed this message was originated by Bob. So that is kind of the whole idea of PKIs. Now, this is relatively abstract. I will now talk about more concrete application of PKIs. In particular, PKIs, or in this case, the web PKI, can be used to initiate secure connections with any entity in the internet. So whenever you use the internet today, essentially any connection is secured via HTTPS and thus indirectly secured via the web PKI. So the web PKI works as follows. Imagine we now have a web server, for example, the Google web server. The Google web server creates such an asymmetric key pair consisting of a public key and a secret key. Then Google contacts the web PKI and tells the web PKI, please give me a certificate stating that indeed I am the owner of the google.com is associated with my public key. If I'm now Alice and I want to visit google.com, I type google.com in my browser. I create my own asymmetric key pair consisting of a public and a secret key. And then I send my public key over to Google's web server. The web server then replies with its own public key. And importantly, it also includes this certificate in its response. And this certificate will now allow Alice to verify whether indeed she's connected to google.com or someone else tried to intercept the connection and pretend to be google.com. And now we come to another interesting cryptographic property of these public and private keys, which is that you can combine them in an interesting way. So Alice can combine her secret key and Google's public key to generate a key K-shared. And on the other side, Google.com can do the same thing. It can combine Alice's public key and Google's own secret key to obtain the same K-shared. And importantly, with the public information available, so this public key of Alice, the public key of Google, and the certificate, you're not able to infer this secret key. So essentially what Alice and the web server now achieved is they have a shared secret key, which can subsequently be used to create a secure tunnel between them. So they can essentially encrypt any message they send to each other and also authenticate it. And no other entity can inject messages or delete messages or forge other messages. So as I said, this is very commonplace. Essentially, you do this every day, hundreds of times with your smartphone or your laptop. So in this presentation, I will not focus too much on these applications of PKIs. I will more focus on the fundamental properties that PKIs can give you, and in particular, their trust models. So I just assume that there are very useful applications of a PKI, and I will focus on these two parts. The first part is how can the owner of google.com request a certificate, and how can we ensure that only the owner of google.com gets such a certificate? And I will focus on the other side of the spectrum where Alice validates these certificates. So let's go into how can an entity request a certificate from the web PKI. So we have a similar scenario as before. We have, again, Bob, which is the owner of this domain. In this case, it's google.com. And again, we have Alice, who wants to establish a secure HTTPS connection to this server. The most important entity in the web PKI are certificate authorities, or CAs for short. And the job of a CA is to ensure that it only issues certificate to the rightful owner of a domain. So let's say Bob contacts the CA and tells the CA, please give me a certificate for google.com. The first thing the CA will do, it will perform a domain control validation. So the CA has to ensure that Bob indeed controls google.com. And there are actually a lot of different ways you can do that. One straightforward way is if Bob can show that he controls the web server, for example, by adding a random challenge at a certain on this web server in a certain path, or if Bob can show that he controls the name server associated with google.com, then that can be used by the CA to ensure that indeed certificate can be issued. There are also more manual domain control validation methods, and that has been there have been a lot of controversy and talk about which of these validation methods are actually secure or not, because some of them date back to 20 or even 25 years ago. So, for example, you can actually do domain control validation via phone call, which seems very obscure and strange, but due to legacy reasons, it's still possible. I don't think a lot of CAs use phone calls to validate domain control, but it's potentially possible. But in this presentation, I won't really focus on this. I think I could talk 1 hour about just the domain control validation aspect, but I will focus more on the fundamental properties of the web PKI. Okay, so now that the CA has validated Bob's control over google.com, the CA will create a certificate similar to what we've seen before and send it to Bob. So this certificate is essentially, as we said, a binding between the domain google.com and Bob's public key. Bob can then deploy the certificate on his web server, and with this HTTPS protocol we've seen before, Alice can now create a secure tunnel to the web server and ensure that any data she sends to the web server and any data she receives was sent to the correct destination. This is essentially how the web PKI was designed 25 years ago. However, there is one big issue with this approach, which is there is no transparency. So what happens if, for example, the certificate authority is malicious? What if it issues a wrong certificate to Bob, and Bob then uses this wrong certificate to trick Alice into connecting to the wrong entity? In that case, only 3 entities will know of this certificate: the CA who issued it, Bob who misused it, and Alice who was attacked. But if Alice doesn't propagate this certificate to someone else, for example, an external auditor, the world will never know that this hijack happened. So this has been a big issue roughly 15 years ago with a certificate authority called DigiNotar, which issued several of these fake certificates, which led to the deployment of a system called certificate transparency. And certificate transparency is very straightforward. It's a public log where you can upload any certificate that was issued. Furthermore, it has cryptographic primitives to ensure that it's in an append-only log. So certificates can be added but not removed again from this log. So in today's web PKI, essentially every certificate that you use is also added to at least one of these certificate transparency logs, which means that an external entity can now inspect the CT log and find, for example, a fake Google certificate and then revoke it. It also helps cleaning up the web PKI in a sense that if CAs are frequently misissuing certificates, you can find proof of this misissuance in CT, and you can then remove this certificate authority from the web browser. So these are the basic building blocks we need. And now let's look at the trust model of the web PKI. So as I've said before, the whole security of the web PKI lies in its certificate authorities. And the trust model of the web PKI is that you have several dozens of certificate authorities in an oligopoly model, which means that any of these certificate authorities can issue a certificate for any domain. So I listed here 6 of the largest certificate authorities, and you can see there is a Google Trust Services. So it would be natural to assume that Google Trust Services would likely issue a certificate for google.com. However, due to this oligopoly model, actually any of these CAs can issue a certificate for google.com. And this property leads to a concept called weakest link security, where an adversary doesn't need to compromise all of these certificate authorities. It's enough to compromise any of them. So for example, let's say maybe DigiCert has a weak domain control validation methods. If the adversary can abuse this method, he can get a certificate for any domain. And in our work, we try to mitigate the issues of the weakest link security. But to illustrate why this is actually problematic, let's look at some concrete attacks and problems related to this security property. The first property is quite straightforward. Because of this weakest link security property, traffic interception is essentially possible by any authority. And as I've said before, the DigiNotar attack, which occurred roughly 15 years ago, was a big push towards more security in the WebPKI ecosystem, exactly for this reason. It's suspected that the certificates issued by DigiNotar, the fake certificates, were actually used to intercept traffic to, I think it was Google websites. And unfortunately, this problem is not solved. You can see below, it's a bit small, but there was also an alleged wiretapping attack using such a fake certificate on a Russian messaging service last year. Another big issue of weakest link security leads to the fact that it's very difficult to innovate on the security properties of the WebPKI. If you think about it, let's say you have your own certificate authority, you really care about security, you want to protect your users, so you employ only very strong and very resilient domain control validation practices, right? So nobody can claim a certificate for a domain they do not own. However, if I, as an attacker, will simply go to any other of the dozens of certificate authorities and get my fake certificate there. So it means that in order for a new security measure to actually be effective, all CAs have to implement it, which is a huge, which takes a lot of time. It takes standardization. It can take years or even several years in order for a new security measure to be effective. Yes, please.
So how can a new CA get certified to issue these certificates? There must be some sort of public body, right?
Exactly. I think, yeah, so let me quickly finish this point, then I will come back. So the question is, who actually decides what is a certificate authority, right? That's a good question. And there are certain organizations called root programs, which moderate this set of certificate authorities. And of course, they have their job is not easy because they want to ensure that they don't exclude certificate authorities for unnecessary reasons. So for example, you have certificate authorities which are simply there for legacy reasons because devices cannot be updated. They are hard-coded to use certain CAs, so they cannot be easily be removed. Furthermore, this is very interesting. I will talk about this a bit later. These root stores, the set of CAs which are trusted, are more recently also becoming subject to laws and regulations. So there is an interesting case for the European Union trying to more actively impact the selection of certificate authorities, essentially. Yeah, so that's, I think, an important fact, and I think we can, in the end, discuss a bit more about the selection of CAs and who should be able to select them. Should it be the policymakers? Should it be the browser vendors? Yeah, it's an interesting question. I would like to quickly highlight on kind of the timeline on research on PKIs. So here you can see several PKIs itself. So for example, we can see the web PKI, which was developed in 1998 roughly. There's DNSSEC, which is another PKI I will introduce later. And there's like RPKI, which is yet another PKI. And you can see that in 2011, which is when this famous DigiNotar attack happened, suddenly a lot of research on PKI started to build. Google started to push for certificate transparency to make sure that attacks can be detected later on. But at the same time, research also thought about how can we actively prevent attacks instead of only detecting them after they have occurred and after damage has been done to the victims. And I want to highlight these 4 research proposals. The first is sovereign keys. Then we have polycert and ARP-key, and finally FPGA, which I will present later. And the main goal of all of these protocols is to exactly defeat the weakest link security property. But now that we have seen what the issues are, let's think about solutions. So one of the most straightforward solutions we could think of is, let's say we have this root store, this set of trusted CAs, and we already have an idea of which CAs are probably legacy CAs or are not really doing domain control validation in a correct way. So what if we simply remove them from our root store? And you can actually do this today. You can go into your Firefox or Chromium browser, you can go to the settings, and you can just remove any CA that you think doesn't sound trustworthy. The big problem is that most domains only have a certificate issued by one of these CAs, which means that removing their CA from the trust store means that you can no longer validate or authenticate them. And what does it mean if you can no longer validate them? You can no longer use HTTPS. You have to fall back to insecure plain text HTTP, which is of course probably worse than accepting a slightly less trustworthy certificate authority. A slightly more involved solution would be to use multi-signing, right? You can say, well, we don't want to have a weakest link, so what if we just mandate that you have to present multiple certificates, right? Then even if one of those fails, we still have the other certificates which kind of provide security. And so in this example, we need 3 certificates from 3 different CAs. So Google could have one certificate issued by these 3 CAs and another certificate issued by these 3 other CAs. The issue with this approach is, first off, it increases the complexity of certificate issuance, because you now have to contact 3 different CAs, you have to do domain control validation 3 times, potentially maybe with different methods, maybe not all of them support DNS-based, so it's a lot of effort. And the same thing for revocation. What if your private key gets compromised? You now have to do the revocation 3 times instead of once. Furthermore, one fundamental limitation of this approach is that, or one question for domain owner is, how many certificates would you get? Do you just get 3? But what if a client wants 5? Do you get 5? What if one very security conscious client wants 10? Do you get 10? So the question that becomes, how much effort do you want to invest, and what are the requirements of the clients? And I think the final and probably most problematic reason why I think this is not really feasible is, as I've said before, this root store contains several dozens of CAs. And if you suspect that only 10% is malicious or insecure, that would mean you would already have at least 5 certificates. And if you're a bit more pessimistic, you say maybe 1/3 is not secure, so you will need like tens of certificates, right? Because if you have if 10 CAs are insecure and you have 10 certificates, the adversary will simply target exactly these 10 CAs. So that brings me to the second part of my presentation, which is the concept of trust flexibility and how we can leverage this concept in the flexible PKI to solve some of these issues. So when we looked at these problems a few years ago, we felt that the problem is that we have this fixed oligopoly of CAs, and that ideally the user should be able to specify which CAs are trusted to which level. So this is what we mean with trust preference. It allows a user, for example, to state that I do trust all CAs, but actually I trust the CA X a bit more than CA Y. So the reason for this could be diverse, right? It could be that I'm located in the US, so I trust US CAs more. It could be that I believe in automated domain validation, so I only support CAs which do provide domain validation and don't use phone call-based validation. At the same time, you might have another group of users which has an opposite view of the world. For example, because they are located in different parts of the world, because they feel like automation should involve humans, because then it's more resilient, right? Because a system is more likely to be fallible. So as you can see, it's very difficult to have one view of what is the security of a CA, or which CA is more secure than another. Furthermore, you might have users which say that they do trust some CAs with very high degree, but only for certain resources. So I'm fine with trusting a government-operated CA to issue certificates for government websites, right? Because they're closely linked. They maybe have internal channels which can ensure that there's no domain convalidation. It cannot be circumvented. But maybe I don't want to trust the government-operated CA for all domains, right? So with trust flexibility, you can also scope the trust for certain domains or a subset of domains. And finally, I think that's a very neat use case, which is a bit more niche, but I think it's worth mentioning. Imagine you're in a company and they have a known, kind of like a local route. Like a local certificate authority, which they only use for government, for their corporate resources, right? For example, for the intranet. Some companies might say, please install this route into your browser, so you can also validate company internal resources. However, that's very dangerous, because then suddenly they could also validate external resources, like your connection to your Gmail or your connection to Facebook. So in order to prevent this, using trust flexibility, we can actually accept this self-signed local certificate authority, but restrict it to a subset of resources. Or in this case, we could say, well, I do accept certificates signed or resources signed by this certificate authority, but only if no other certificate authority signed it, which is the case for company internal resources. So now that we have this concept of trust flexibility, the question is, how can we actually implement this? How can we design a system which allows us to create these statements and then also validate our certificates according to this preference? And that's what we did in our work on the flexible PKI, FPKI. So this was actually submitted at NDSS in 2022. So if you want to know more details, please take a look at the conference submission. So here we have the same system we saw before. We have the web PKI, including the certificate transparency, which logs all certificates. And we have the web server, and we have Alice validating certificates. FPKI now introduces an additional component called the FPKI server. And the job of the FPKI server is to aggregate certificates based on the certificate transparency information, and aggregate them based on their domain. So the FPKI server will periodically query all of the different certificate transparency logs, fetch all certificates, and then essentially order them in a data structure which is similar to a dictionary, where the key is the domain name and the value is the set of all certificates which are valid for this domain name. Because what this allows Alice to do, Alice can then fetch all certificates for google.com, and the FPKI server can look up into his dictionary, see that there are 2 certificates that were issued for google.com, and give them to Alice. Yes.
Like before, you said that there's this weakest link problem, and one solution is to just require multiple certificates, but that comes with like these additional costs. But here you also have multiple certificates, right?
So you can have multiple certificates in the current web PKI. So one reason might be you have different servers, so they all deploy different certificates, different public keys. So it's not per se a violation to have multiple certificates. It can just be the case. And actually, interestingly, when we did like real world measurements, we saw that Google did have actually a large number of certificates for different subdomains and so on. So yeah, that is definitely the case, can be the case. So once Alice has fetched all certificates for a given domain, she can then verify based on her trust preferences and this certificate landscape, so all certificates that exist, whether she wants to accept the certificate presented to her during the HTTPS connection. And that sounds maybe a bit complicated. I will try to make 2 examples to make it a bit more illustrative. So let's look at the following scenario where we have Alice and Bob again. And again, they have conflicting views. They have exactly the opposite view. So Bob trusts the blue CA more than the red CA, while Alice trusts the red CA more than the blue CA. And we'll show how FPGA can incorporate both of these trust views. So imagine Google gets its certificate from the blue CA. So the Google domain operator contacts the CA, gets a certificate, and it serves it to both Bob and Alice. Bob will immediately accept this certificate because the blue CA is his most highly trusted certificate authority. So of course, whenever he gets any proof by this CA, he will immediately accept. Alice, however, is not so sure, right? What if there is actually a certificate issued by the red CA, which she would prefer? Which means to ensure that that is not the case, Alice will contact this FPGA map server that we've seen before, tell it, please give me all certificates for google.com, and the map server will reply with this single certificate which exists. And because Alice now knows that the red CA didn't issue any certificate, she will accept the connection and continue connect to this domain. At the same time, FPGA prevents downgrade attacks. Again, we have the user Bob, which trusts the blue CA more than the red CA. And we again have the certificate issued by the blue CA. But now we also have another certificate, a red one, issued by the red CA, which is actually a fake certificate. So as I've said before, the reason for a CA issuing a red certificate could be that it's actively malicious and tries to perform an attack on google.com, but it might be that it's just not so diligent in its domain control validation, or that the attacker used some network attack to trick the CA into issuing the fake certificate. If Bob now receives this red certificate, similar to what we saw with Alice before, he will not be sure whether to accept it or not. And he will connect to the FPGA server, and the FPGA server will tell him, actually, 2 certificates exist for Google, one issued by the blue CA, one issued by the red CA. And based on this information, Bob can then decide that this looks like a hijack attack, like a man-in-the-middle attack, and reject the red certificate. These are kind of the 2, I would say, main properties that FPGA allows users to do. And I would like to quickly also highlight some challenges in FPGA. And the first one is the deployment. So we do require changes at the user, right? Bob has to additionally fetch these certificates from FPGA server, and then it has to locally validate and potentially check the connection. So that is a requirement. One good way to overcome this challenge is actually to use browser extensions, because all of the functionality that we need is exposed to a browser extension. So we actually implemented FPGA as a browser extension, which you can just download and enable in your browser. The other challenge is availability. We do require this FPGA server to have a high uptime and to be reliable, because what if you cannot connect to your map server? You would essentially have to wait until it's responsive or accept the risk of a downgrade attack. So there's this kind of trade-off that's really relevant. A better solution would be to allow the web server to give you this certificate landscape directly during the HTTPS connection. This is a concept called stapling, right? Which would mean you don't need any additional connection to another out-of-band entity. However, this does require changes at the web server. So these are just some of the challenges that the FPGA exhibits in the regarding deployment. Next, I would like to briefly compare FPGA to other PKIs and their trust models. And I would like to start with DNSSEC. DNSSEC is very interesting to me because it essentially operates on the same, in the same namespace as WebPKI. So WebPKI creates bindings between domain names and public keys, and DNSSEC does exactly the same. It creates bindings between domain names and public key, just in a slightly different fashion. So here on the left side, you can see how WebPKI operates. We have this oligopoly model of several certificate authorities, which are all trusted to issue certificates for the entire namespace. On the other hand, we have DNSSEC, which has one single certificate authority as a root. And this certificate authority then delegates control to different namespaces. That's something you have seen whenever you type, for example, google.com. It's actually inside the .com namespace. Or if you go to fbi.government, it will be in the .government namespace. So each of these namespaces essentially has its own CA in a sense, because, for example, the .com certificate can then issue other certificates for subnamespaces, for example, a.com or b.com. So if you look at this model, it's essentially hierarchical, which means that we place a lot of trust into this root, because this root could essentially claim the whole namespace. However, we place slightly less trust into the .com root, because it can only claim the .com namespace, and so on. So I would argue that the biggest issue of the WebPKI is its weakest link security that we've seen before, while the biggest weakness of DNSSEC is its inflexibility and single point of failure. And there's also an interesting point regarding governance, because who controls the private key associated with the DNSSEC root, right? This is one single private key, so who should be able to govern it? And yeah, I think there can be made arguments that it's not fair right now because it's owned by a US entity. So people in different countries might argue this. I want to quickly put this into perspective of FPKI. What we did in FPKI, we tried to avoid these weak links, and we tried to create more flexible certificate hierarchies. Right? Kind of a user can define which CA is trusted more than another. So you could essentially emulate the model we have on the right side, but it's decided by the user whether they want to use such a model. Next, I would like to do a small detour into a different kind of PKI, which is a routing PKI. So in a routing PKI, what we are securing are not domain names, but routing resources, so IP addresses and autonomous system numbers, where an autonomous system might be Verizon or AT&T. The routing PKI for the current internet is called RPKI, the resource PKI, and it's also based on an oligopoly model similar to the web PKI. But the difference is that each of these routes has its different namespace. And inside this namespace, we again have this hierarchical delegation of resources. So for example, one of these routes would be the European route, one would be the North American, the South American, and there's the African and the Asian route. And all of them govern their respective IP addresses and AS numbers. Then I would like to quickly mention another internet architecture called Cyrill, which I have worked a lot on in the past. And it has its own public infrastructure, which is actually relatively similar to RPKI, probably because they both operate on network resources, which are structured similarly in this current and this future internet architecture. In particular, we also have different namespaces. The main difference is that each namespace has its own local trust anchor, right? While in RPKI, we have this oligopoly. In Cyrill, we have per namespace roots of trust. And these roots of trust can update themselves. For example, if one of these CAs gets compromised, they can just replace it with a new CA. And inside, one important property in the Cyrill PKI is that as a user located in one of these namespaces, so for example, me as maybe as an AT&T user, I only need to trust AT&T's trust anchor. And then from this trust anchor, I can automatically infer trust to the rest of the network. So you only have to trust local entities, and then you can kind of expand the trust from there. And finally, delegation to different resources like AS numbers is done similarly to RPKI. So if we compare these two models, they are very similar, but the main difference is that the Cyrill PKI has a smaller namespaces and also more independent namespaces. And if we put this into context with FPKI, of course, we now work on different namespaces. It's not domain names, it's IP addresses. But one conceptual difference is that in FPKI, we have trust levels, which we can enforce through proofs of absence. We have seen this before. If Alice knows that her highly trusted CA didn't issue a certificate, she will gladly accept a certificate issued by a less highly trusted CA. So this concept doesn't exist here, probably because they have these different namespaces, which don't make it that useful. Next, I would like to quickly talk about Web of Trust, which is essentially a distributed public key infrastructure. In Web of Trust, the CAs are the actual users of the system. So, for example, me here could be a user which validates all the public keys of his contacts. Maybe he meets them and then he scans a QR code on their smartphone. And then his contacts again can verify their contacts. So from my contact of me here, I can create chains to his contacts and so on. So ideally, I should be able to reach the whole world or a large part of the world by following these trust chains. Of course, the main issue is most people are not really suitable to do the diligent work of a certificate authority, right? Most devices can be compromised or people might just randomly add other people. Furthermore, one big challenge is how long do I allow this chain to extend, right? Maybe I trust me here to be diligent and don't add people with their own public keys, but maybe his friends might add public keys. But if I limit it too small, I don't have any benefit because I only have my own circle. Furthermore, it's very difficult to interpret the security of a 2-hop versus a 3-hop versus a 4-hop indirection in this system, right? And finally, it's also not that easy to use. You have to synchronize with your different devices, with your email accounts and so on. In FPKI, we actually have a similar property where we have local trust into different entities. But what we try to ensure in FPKI that we always have a binary validation outcome. So at the end of the FPKI validation, you either have accept this certificate or reject this certificate decision, nothing in between. And also the trust preference in FPKI can be reused, but in PGP or in Web of Trust, they are very personalized. So I cannot simply take someone else's list of contacts and use them to secure my contacts. Finally, that's the last slide I have is on self-authenticating identifiers, which are another way of key authentication, but it's very different because it's not really infrastructure. It doesn't need any external entities. And there are two examples there. One is the Tor anonymity network, where the idea is you don't have any certificate authorities. Instead, you encode your own public key into the name itself. So your name, your DNS name would essentially be hash of the public key .onion. And a similar concept is used for CGA, cryptographically generated addresses, where you encode your public key into your IPv6 address by using the lower bits of the IP address. Of course, this is in a sense an ideal infrastructure because you don't have to trust anyone. However, there are several challenges, one of them being the key agility. So if everybody knows the hash of my public key, and now my private key relating it gets compromised, I have to update. So I have to inform all of my contacts, please also update my identifier. So since the identifier is tied to the public key, it's very difficult to update them. And one other big issue is that public keys are not really human readable. For us, it just looks like a random string of bytes. There's one interesting work by Paul Syverson, who's also been here on the WebPKI workshop 1 year ago, or 1.5 years ago, where he proposes that self-authenticating identifiers are ideal, but we somehow have to bootstrap them. And his approach would be to bootstrap them via the web PKI. So initially you trust the web PKI, but once you have done the bootstrapping phase, you are now in the secure world of onion addresses. And I think that's also where FPKI could come in, because FPKI can be used to strengthen the web PKI. We could use it to strengthen this bootstrapping phase to, in the end, transition to self-authenticating identifiers. With this, I'm already at the end of my presentation. I do have some discussion points prepared, which I think would be interesting, but maybe if someone has a question right now, please feel free to add them. To ask them. Yes.
Hi, thank you so much for the talk. This was very interesting. One thing I was curious about is in the case where, for instance, you showed the preference of, say, a blue certificate over a red certificate, and therefore I kind of deflected a hijacking attack if the red certificate was actually not a valid certificate.
Yeah.
In the process where I'm contacting the FPKI server, is it possible that a hijack could also occur there? And I could, if I were an adversary, I could just drop the blue certificate and say red's the only one.
Yeah, that's a very good question. Yeah, definitely that would be an attack on the system. So I simplified FPKI quite a lot because I didn't have time to go into more details, but this certificate landscape that the FPKI server provides to Alice or to the user is actually protected via signature itself. And it's quite interesting. It uses a sparse Merkle hash tree to ensure that we can also prove that no certificate exists for a given domain, right? If I ask for randomstring.com, FPKI server will tell me, hey, nothing exists, and here's a cryptographic proof that really nothing exists. Yeah, that's a very good point. We need to secure this channel between the FPKI server and the user, otherwise we don't get any security benefits.
Thank you.
Yeah, please.
Thank you so much. I think a related question is, I was wondering if you could explain the intuition behind why, if Alice's like most preferred CA isn't there, but like the second preferred is, like if the red really is there, and we have this now secured thing saying that the red is there and the blue's not there. What is like the intuition behind why Alice should then accept the red certificate, like the second most preferred?
So if both highly trusted and not so highly trusted exist, why she should prefer the highly trusted?
Oh no, if the highly trusted doesn't exist, but the next highly trusted.
Yeah. So in the end, it becomes a question of what is how does Alice evaluate the trustworthiness of these CAs, right? And of course, this trust preference must reflect Alice's actual reasoning, right? So if Alice prefers one CA to the other, the meaning is if the website could be secured by the more highly trusted CA, definitely she wants to have this level of security, right? If you would then allow to say, well, maybe this domain has two certificates, then you could not distinguish this case from the case of a downgrade attack. Again, I kind of simplified some aspects of FPKI. We also provide the idea of creating a policy where the domain owner can explicitly specify if he wants to have certificates from different CAs, because in some cases, a domain owner might want to have both a GTS, a Sectigo, and maybe DigiCert certificates. So we also provide a way to kind of describe this information and allow users to then use either of these CAs. But just based on the trust preference, you would then have to reject the less trustworthy certificate. I hope this answers the question.
Where are these trust preferences coming from? Like I personally don't have one.
Yeah,
and I think most people in here don't have one.
Yeah, maybe I can quickly go through one of the discussion points, because that's, I think, one of the big challenges.
Like perhaps related to that, if those trust preferences are somewhat static, don't you sort of lose that oligopoly oligopoly benefits, because like if everybody has the same trust preferences, then
Even if I would argue, even if everybody has the same trust preference, we still get benefits from the system.
Okay.
Because let's say we have a very neutral trust preference stating if you have very secure domain control validation, you get a higher trust level than if you use phone-based domain control validation. If everybody relies on this, then we can still get benefits, right? We kind of deprioritize the phone-based validation and make sure that it's only used if it's really necessary, right? So this system, FPGA, can have a lot of benefits, in my opinion, even if we have one global trust preference. But I think the real benefit comes when you also allow personalized trust preferences. But let me maybe go through the discussion quickly. So the first point I think could be interesting to discuss is the intersection between policymakers and the webPKI, or I guess FPGA. And I think the question there would be, what should the responsibility of policymakers be? So the root programs are currently managed by for-profit organizations. So some people, for example, the EU government, may argue that that's not how it should be, right? It should not be a for-profit organization managing the trust of essentially all of internet communication. And I think policymaker could also promote implementation of new security systems. And using FPGA, we could also make government-related web resources more secure by giving a preference to government CAs for these resources. And in general, drive security innovation with new security measures. I'll just quickly go through them, then we can discuss. I'm not sure how many of you know about this. So the European Union recently created a new law which states that essentially any browser used in the EU must include their certificate authorities, even if it may not apply or comply with their standards, right? So the problematic aspect, in my opinion, and the opinion of many research, is that this essentially dictates an upper level of security, right? Instead of saying CAs must be at least this secure, you say that's secure enough, and you're not allowed to enforce more strict security. And the fear of many people, of course, is if this happens, for example, these CAs might not use certificate transparency, which may lead to more stealthy man-in-the-middle attacks. It might also lead to unfair advantages because a EU CA might not have to comply with the strict requirements of a US CA. And I think that's also a point where FPGA could be interesting, because it could essentially prevent these downgrade attacks. You could say that the more highly trusted CAs which apply to more higher levels of security also get a higher trust level. So the EU CAs which are not so secure could not downgrade their protection. And I think what you mentioned before, the selection of trust preference is crucial. Like most users will not be able, even me, I will not be able to make a very educated guess on the CA. So there needs to be some form of automation or an easy way to do, for example, download trust preferences from policymakers or also from trusted organizations. So the Electronic Frontier Foundation might be a good source of this, right? Because they try to be independent, they try not to be biased by different governmental ideas. Yeah, and we could make sure we have more objective security properties for these trust levels. And one last thing I think is interesting is the concept of centralization and decentralization. I have been looking at attacks on cryptocurrencies recently, and what I think is interesting that blockchains and Web3 always try to provide more decentralization in security and improve it, but in the end, what is being attacked is the centralized aspect of access portals or wallets or configuration files, which are protected with the webPKI. So I think even if we have new security concepts like blockchain, we need to make sure they're not hindered by legacy system like the webPKI. That was a bit longer, but yeah, if there's anything interesting, discussion points to discuss, please. feel free.
It's not on those discussion points, but
Yeah.
something I like makes me wonder is you said to do the whole FPKI, everybody needs to download a browser extension and then everything's just perfect. Now I doubt that everybody wants to download a browser extension.
Mhm.
So like the whole proposal seems very unrealistic from the start.
So the reason why we went for a browser extension is because it has all the necessary functionalities, and it allows us to test it and allows people to opt into the system and use it. Ideally, this functionality, in my opinion, should be implemented by the browser itself. It should come with the browser. And the browser, as I said before, might have a default trust preference, which already is better than the current WebPKI. And then a user can furthermore bring its own preferences inside and make it more individual. But I agree, right now you need to download the extension, but it's actually quite straightforward. You could just, with one click, you could download. Yeah.
Based on all the work that you've done in this area, what do you think is the best trust preference hierarchy for schema?
So generally, I would go for kind of the bottom left, look at objective security properties, because I think that brings the most benefits. I'm not really sure if I'm from Switzerland, if I would trust a Swiss CA much more than a CA from many other countries. I think that's a bit, it doesn't bring so much benefits. But if you have if a CA clearly states they will only use the secure methods, they have a lot of safeguards and defenses against networking attacks, then I do trust them much more than another CA which just does the bare minimum. So one interesting approach could be that in the standardization, right now we have a minimum level, right? We have minimum level that every CA has to adhere to. It could be interesting to have like different levels, like how much a CA invests into security, and the more they invest, and that could be audited, the higher the trust level could be. So I think that would be an interesting starting point to kind of promote more secure CAs.
Who is setting the minimum standard?
This is an entity called the CA Browser Forum, which is essentially a collaboration of different CA operators, and I think also the browsers are, the major browser vendors have a lot of say into how these standards should be defined. And just this morning, unfortunately, it was a bit late, I found a very interesting article, this one here, which talks about this EIDAS rule, this Article 45, which might include like European Union government CAs into the WebPKI. And I think it's very interesting because they say that the WebPKI is not really good the way it's operated right now. It's not really transparent, and some of the incentives don't align. And also what EU proposes is not good. So they kind of analyze these two ideas and then try to give directions of how in the future we should actually implement it. So if people are interested, I think we could use this in one of the reading sessions, because it's not, I think it's not that complicated to really see the trust relation.
All right, well, thank you so much.